Hello, class. In this lesson, we are going to look at different physical properties and how they relate to the intermolecular forces that a molecule experiences. First thing I wanted to do was look at this periodic table. This is a great periodic table that is interactive from the Royal Society of Chemistry, which is rsc.org, periodic-table, if you want to experience this for yourself. At this point, I have set the temperature to be 25 degrees Celsius, which is what most people consider to be room temperature. It's about the equivalent of 77 degrees Fahrenheit, so it's a tad warm. And it's also, we've got the Kelvin temperature, which is 298 Kelvin. We have not talked about Kelvin temperature much at this point, but we will talk about it in detail today. So take a moment and look at this table and make some observations. What is the predominant phase of matter at 25 degrees Celsius? By phase of matter, I'm talking about solid, liquid, and gas. As you can see, the majority of these are light blue. So most elements are solid at room temperature. There are a handful that are gases, those are in green. And then in the darker blue, there's only about 3 of them that occur in a liquid state. If I play around with these temperatures a little bit more, I've got this temperature slider at the top. As I increase the temperature, you'll see that we see a transition from the number of solid to number of liquid and then even gas compounds at room temperature. So as I increase my temperature, I'm getting up into thousands and thousands of degrees Celsius. I'm starting to see a ton more liquid and even more gas compounds or gas elements. Apologies. If I keep increasing the slider and make a prediction, what type of phase of matter will we see? Well, if I increase it all the way, eventually everything will exist in the gas form. So at higher temperatures, things tend to exist as gases. At lower temperatures, things tend to exist as solids. So when we're at 0 Kelvin, just about everything exists as a solid. As I increase those temperatures, we start to transition and we see this boundary between solid, liquid, and gas. These phase changes are really important. We're going to look at them first through this fast enough for you reading. So I'm not going to read the entire thing, but I am going to talk about some of the key points. I want to jump to the end of this first paragraph. They talk about temperature, but in science, temperature refers to speed. So we want to talk about molecules and how they move around. Molecular motion's the key idea that's going to be the backbone of everything we're looking at today. So we know that as we study molecules, they will bounce around and they'll constantly bump into each other. As they bump into each other, we call this a collision. Energy is transferred between molecules when they collide. The average kinetic energy, kinetic meaning motion, so the average energy due to motion, in any sample is related to the temperature. Even though the speed of individual molecules may change as they collide and transfer energy, the average speed or the average kinetic energy will remain the same. This is a key idea at the end here. Higher temperatures result when molecules collide with each other at faster speeds. So, in essence, a higher average kinetic energy, I'm going to abbreviate kin energy, means a higher temperature. So in this reading, they talk a little bit more about gases and liquids. So as we heat things, we know they expand. So gases and liquids expand when they're heated because the molecules are going to be moving faster because they're at a higher temperature. So The important thing to recognize here is that things that have a higher temperature are most likely to be gases because they have more molecular motion and more energy between the particles as they are moving. Temperature is not a measure of heat, it is a measure of the average kinetic energy. Okay. When we go through and look at some of these diagrams, it's important to keep that in mind. When we increase our temperature, we increase the molecular motions. But what's also interesting, if we look at diagram 2, is that as we increase molecular motion, we're decreasing molecular interactions. What I mean by that is the amount of intermolecular forces experienced between molecules decreases as we increase the temperature. It takes energy to pull these molecules apart. If you think about intermolecular forces, like the glue that hold molecules together, right? IMFs are like glue. And if we increase the energy between molecules, so if I had two molecules that are interacting with each other, energy has to go in to separate that attraction. So this is just some random molecule, some other random molecule. As we increase the temperature, this interaction becomes broken, they separate it, and then they can transition from a solid phase to a liquid phase, or maybe even from a liquid phase to a gas phase. When we get to this gas phase, you see those molecules and those atoms are not even touching each other. They are very far apart. Here, you can still have a bunch of tiny interactions in between these. And in the solid form, you have a ton of intermolecular forces uh, keeping those molecules together. So let's recap. Which state is most likely to have the strongest intermolecular forces? Well, it's the state where the molecules are closest together and can have interactions with each other. The strongest intermolecular forces are when we are in the solid phase. The weakest intermolecular forces are when we have the least interaction with each other. That would be our gas phase. It also says intermolecular forces are used to explain physical properties such as melting point and boiling point. Which kind of substance likely has the lowest melting point? So, the lowest melting point would be the thing that melts the easiest. So, the thing that melts the easiest is the thing that has the least amount of intermolecular attractions. In nonpolar covalent, we have LDF only. In polar covalent, we have LDF, dipole dipole, and then sometimes H bonding. And then in ionic, we have LDF and ion ion. So we know ion ion is one of the strongest, so those would have relatively high melting points. Dipole dipole and H bonds are much stronger than LDF only, so those would also have higher melting points. The lowest melting point would belong to nonpolar covalent compounds because they have dispersion forces only. The whole goal of this lesson is to be able to explain those physical properties that we see by identifying our intermolecular forces. So we're going to go through and do a couple of practice problems. In my classes, I gave a packet a while back on intermolecular forces. This is basically a modified version of that assignment. So there is additional practice in that packet for you. First thing we need to do is identify the intermolecular forces. I see CH2F2. Those are all nonmetals. And so, since they're all nonmetals, I have to consider the types of bonds that would be in there. In that particular molecule, I know I'm going to have CH bonds and CF bonds. One of those bonds is going to be nonpolar, the other one is polar. So I think it's safe to say this is a polar compound because there's an imbalance. There's a combination of polar and nonpolar bonds. When I'm looking at neon, Ne, that is a single atom. It's not bonded to anything. You can treat single atoms like nonpolar molecules. And then when we look at water, we know water has polar bonds. It will also be polar. Every single molecule is going to experience London dispersion forces. And then we just have to go through the breakdown. If I compare the bond types, CF is polar and OH is also polar. But the OH bond, we know, allows us to experience hydrogen bonding. So not only do we have dipole-dipole for my polar water molecule, I also get H bonding. When I look at my polar CH2F2, I get dipole-dipole only. If I'm trying to evaluate the molecule that has the highest boiling point from this list, it's going to be the one with the strongest intermolecular forces. So in this case, water, and the reason why is due to stronger IMFs. The lowest boiling point would belong to the one that has the weakest IMFs. In this case, it would just be neon, since it experiences London dispersion forces only. I can go through and look at some other examples. In this next one, number 4, we have NaCl, which is an ionic compound, because I have a metal and a nonmetal. And we have sugar, which is a polar covalent compound. If I'm looking at the intermolecular forces here, I know that in an ionic compound, I have LDF and ion-ion. In sugar, I will have LDF and dipole-dipole forces, and probably even some H bonding forces, if I had to make an assumption. I would have to actually look up the Lewis structure for sugar to double check that. But even so, I know that ion-ion attractions are much stronger than dipole-dipole and H bonding attractions. So just the fact that it is an ionic compound is enough for me to say it's going to have a higher melting point. In this next one, I'm looking at gasoline, which is made up of carbon and hydrogen bonds, and methane, which is also carbon and hydrogen bonds. So this one, they tell us that one is a liquid and one is a gas. But what's interesting is that they both are made up solely of CH bonds, which are nonpolar. So here we have to compare the strengths of the London dispersion forces. So since they both experience LDF only, you have to look at the number of electrons that each atom has. So we know that we can use our atomic numbers. So carbon has an atomic number of 6 times 8 atoms. 6 times 8 is 48. Plus the atomic number of hydrogen is 1 times the 18 hydrogens we have. And so this gives us a total of 66 electrons. When we're comparing that to CH4, CH4 just has 6 plus the 4 hydrogen, so it has 10 electrons. Even though these both experience only London dispersion forces, there are more electrons in gasoline, which means the strength of the temporary dipoles they experience is much higher. Since there's more electrons, it's considered to be more polarizable, is the word we're going to use. And more polarizable just means it has a stronger temporary dipole. Since there's a stronger temporary dipole, there are going to be increased interactions and is going to allow them to stick together and be liquid at room temperature. Keep in mind that a liquid has stronger intermolecular forces than a gas. Okay. And then the last one we're going to look at today also involves us looking at some data. I love problems like this because you see trends in data that don't always match up with what you'd expect. Here it says, explain why as you move from bottom to top of this table, boiling point decreases, but then increases for H2O. If the boiling point is decreasing, that would tell us that we have weaker intermolecular forces. A lower boiling point means that it is easier to separate our molecules. So keep that in mind. Low boiling point is easier to separate. Therefore, low boiling point is easier to separate, and therefore the IMFs will be weaker. So if we look at the compounds here, they all have the same general structure. They're all bent molecules. They're all in the same group. They all have the same valence electrons. So in terms of, should be an S, I'm sorry. In terms of their structure, they're all going to look the same. Now, what you'll see though is that there's this change in mass. If there's a change in mass, that's pretty well correlated with a change in number of electrons. So as the mass decreases, the number of electrons, E minus, decreases. Therefore, we'll see weaker IMFs and a lower boiling point. That's how we can explain our trend for those first three, but then think about why water might have a much higher boiling point than the rest. Well, water is polar. It's got London dispersion forces, it has dipole-dipole forces, and it has hydrogen bonding forces. Hydrogen bonding forces are much stronger than dipole-dipole forces on their own. Whereas these three molecules only have polar bonds, or maybe even some nonpolar bonds, depending on the electronegativity differences. The OH bond is going to be very polar. It's going to be H bonded, and therefore it's going to require more energy to separate. The last problem type I want to look at today is actually dealing with ranking the boiling points. So if we want to rank things from lowest to highest, first thing we need to do is classify our elements. So I'm going to look at number 8 here. So we want to classify them as polar, nonpolar, or ionic. And then once we do that, it'll help us to rank them. So I know that NaCl is going to be ionic because it's got a metal and a nonmetal. HCl is going to be polar. N2 is bonded to itself, so it's nonpolar. And HF is going to be polar. Now, I know that ion-ion attractions are the strongest, so NaCl is going to have the highest boiling point. And then I know nonpolar has only London dispersion forces, so I know N2 is going to be the lowest boiling point. Now, to figure out how to classify HCl and HF, I have to see if they have, one, a difference in their intermolecular forces, and then two, a difference in their London dispersion forces. With HF, you have H bonded to F, so this also experiences H bonding in addition to dipole-dipole, whereas HCl is dipole-dipole only paired with its London dispersion forces. So for that reason, HCl, since it does not have H bonding, is going to have a lower boiling point than HF. Now, there are times, as I mentioned in the last video, where you may need to look at how many electrons there are total, because things could be polar, both have polar, dipole-dipole, London dispersion forces, but you also need to look at how many electrons there are to figure out which one would have a greater London dispersion force. An example would be if I were trying to rank PF3 versus HCl. Both of these are polar and experience dipole-dipole forces. If I look at how many electrons they have, I get 1, from hydrogen and 17 from chlorine. So I get 18 total electrons. And then look at PF3. F has 9 electrons times 3, which is 27, plus 15, which gets us uh, 42. When I'm comparing the number of electrons here, 42 is greater than 18. So PF3 would have a higher boiling point than HCl. So sometimes if they have the same intermolecular forces, you'll have to compare the number of electrons in order to identify who's going to have a higher boiling point.